So, welcome, Callum. You're just a couple of minutes late, not many at all. And I'm only really expecting Emmy to come in because Nikki didn't come to physics either. So, I'm just going to begin like I did with similar to what I did in physics. I just want you to be aware that term two is very demanding. You might have thought term one was demanding. Well, now you've got all those skills under your belt, and we're going to go even faster. And I also want you to be aware that in maths, in term one, we spent 10 weeks really on further differential calculus. And today we're going to start continuous random variables. Then we're going to go on to integral calculus. Now, integral calculus is the reverse of the inverse process to differential calculus. So you must understand diff calculus thoroughly. So you really, who feels like both of you, do you go back over your skills and application task and learn and deepen your learning as a result of the results you got? Some of the time. So I just want to emphasize how important that is. And even sometimes you actually do a correct process and get the correct answer, but it's not the most efficient or the most effective. So to look at the solutions that I put in Daymap in your own solution, you might see that I've given you 4 points because you've got it right, but you might say, actually, I could have done that in a more elegant manner and that saves time. But it also, often the more elegant process shows that you understand more thoroughly what's required and you can get there quicker. Um, then, after doing the integral calculus topic, we go back and we look at continuous random variables. So, the topic you're doing now, you must understand thoroughly so that when you come back to it, you can build on it. So, just that awareness of the connectivity of the topic. The other reason that you've got to be super organised is that we're going to do a mid-year exam in the very start of term three. So term two holidays, again, will be pretty busy. Um, so just be aware that that mid-year exam is coming. And so if you look at the SATs that you've done and you correct them, maybe you have a look at the solutions for the questions that you were unable to do, put the solutions aside and use it as a learning experience if there were sections you couldn't do. That will be actually consolidating your knowledge, not just for the topics that are coming. Well, that's the best reason, but also for the mid-year exam. Have you people got someone that you talk to support you with your learning? Now, there's two aspects of that. One of it is sort of emotional and organisational. So that sort of person doesn't have to really know the maths. And then there's support with the maths. So give me a tick if you feel that you've got good support and more than one way of getting support. And across if you're pretty well on your own. Excellent. So use your support people. And use me. What I find is sometimes people get a tutor, which I think is brilliant, and then they stop asking me questions. But um, that's what I'm here for. Okay, so make sure that you use your support. And sometimes you can ask somebody a question and you don't quite get it, and you ask another support person the question and it becomes clear. Nothing against the person who was asked first. It just really helps to have more than one chance to have it explained. And another thing that really brings success is a self belief that even if at the moment you don't understand it, you will understand it. And it also an ability to look back and say, I didn't know that topic and now I do, and I'm proud. Are you guys any good at, feeling satisfied that with a job well done? Smiley face if you tell people that you've done something good. Excellent, Pete. It's something that many people find hard to do. and I also find hard to do. But sometimes you can say, my teacher was happy with me. Like you sort of almost, instead of saying you're happy, you let maybe your parents know that, Janice, the teacher, is happy. So make sure that you give yourself pats on the back because it's a stressful year and emotionally draining as well. But I hope you enjoy the learning and you enjoy new things. So, Emmy, welcome. So just want to check your sound's okay, Emmy. So it's good to have you here. So this topic is going to be on random variables. And I just want you to draw on the knowledge you already have. And in text chat, I'm just going to give you 2 or 3 minutes. Write down words or ideas that come to mind when you read random and continuous data. I hope it works. All right, so as we think and we articulate our ideas, it really brings the knowledge to the front of our mind and it's sort of like a deeper learning. And what you're going to find, I suspect, by the end of the lesson is that your perception is going to change a bit. It might be more detailed or it might be, oh, I didn't quite get it. And all I've written on the board is random and continuous data. I haven't actually talked about random variables. So when I see Pete's comment about random, it made me realise you'd looked at the word on its own and you hadn't actually linked random and data together. So that's my poor language. And what you're going to find with this topic is chasing the language and having a common definition is really important. And following the notation and the fact that different forms of notation are used even within a single textbook. So Hazy jumps around with its notation. If you get confused, try and work it out for yourself, but don't take too long about it. Send off an email and say, why is it said this way once and this way the next time? And I might say, no reason. Okay, it's just inconsistent notation and both mean the same thing. So this lesson is partly going to be, because I think the concepts are fairly straightforward, is partly going to be getting used to the language and the notation. So can you just quietly read the opening problem and can you highlight key bits of information as you read it? And I'm going to talk as you highlight. So when I read that 50% chance of winning a prize, I think in terms of probability, all right? And I immediately change 50% into a decimal because that's the way I think. And probabilities are quite often expressed as decimals. All right, now there's more to highlight. Okay, so we're looking at a variable that is to do with winning the game. So the variable we're interested in has a capital. So capital X is winning, is 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 the prize value. And so the way I worked that out was by actually looking at what they've put in the table. that the prize value is the variable we're examining, and there's a whole heap of outcomes. I might just use this. So capital X, sorry, capital X is the prize value, and then little x, excellent. Could you swap from yellow? The little x's is the outcomes. And in this sideshow, we've got 5 outcomes with those $0 up to $20. And then we've got, so just notice that the little x is actually for the outcomes. And then when we work out the probability, what we're doing, capital P for the probability, we have a statement that the probability that the characteristics we are looking for is one of the outcomes. Let's say the outcome is X1. Then we can read off the probability, it's 0.5. Is there anything else that you notice when you look at that table? All right, so how would you go about working out the chance of winning $20? Excellent. And the way we'd write it down is the probability of the characteristic we're after. Now I'm using capital X, but Y and Z are also used sort of fairly frequently. Is the outcome, we've numbered it number 5, so that's the $20. And yes, it's just a matter of reading it off and expressing it either as 1% or decimal .01. Now, I interpreted that that's the straight probability in theory. If we actually played a lot of games, we might be interested in the amount of money that we are likely to win in the long run. And in that, what we do is we multiply the value, so $0 times the probability, now that's going to give 0, plus $2 times 0.35, etc. And we would work out like an estimated value of what you would win by combining all those probabilities. So if we summed all the probabilities together, so I'm just going to the top of the page because I don't have a lot of room. If we summed all of those individual probabilities, so the value xi or x1 times the probability, all right, from from the number equals I up to n, and in this case, we've got 5 terms, so n will be 5. So what is the meaning if we summed all of those probabilities up? Thank you, Peter. Did everyone hear that word sort of expected to win on average? So often the average is sort of in the word in the long run. So as we do, if we looked at a huge number of games, then we could say we would expect with a fair amount of certainty. So the level of certainty about the reasonableness of our answer actually depends on the number of games or the number of trials we play. So the expectation in the long run, now I haven't summed it up to work it out, but you're going to, half the time you're going to lose. And if you look at the modal value, the most often it's $2. So I reckon it's going to be $1.50 or something in the long run. But you also need to sort of know how much you paid out, don't you? Is getting $1.50 back in the long run worth it if the total cost is $20 or something, you know? Um, but the purpose of playing the game may not be actually to have a financial gain. So those things are all part of it. So there are non-mathematical, there are social and entertainment reasons, as well as simply economic ones. Um, okay. Now, one thing, what I've said is this is only valid if we've considered every single outcome. Have you got any idea how we can look at the data in that table and decide that it's valid data? I'll just change the question a little. Is there any way that we can tell that we've considered every single outcome? And so everybody, do you want to do that? Do you want to do the sum of the individual probabilities? What do we get? You can get out your calculator. Agreed. We get number one. Now, is that what you were expecting? If we considered every single outcome, is one what we expect? Yes, it is. All right. So, if we consider the whole or 100%, we're then 100% written as a number is the number one. So every outcome probability added together will be one. And what that means is all of the individual probabilities have to be between 0 and 1. So just making sure you understand the notation, all the individual probabilities have to be between 0 and 1, and their sum. So can I have a tick? Are you used to using epsilon, which is the capital letter E in Greek? Are you used to using epsilon to mean add up all the parts, all the terms? Just give me a tick if that's familiar. All right, so that's what you've got to look for. You've got to make sure as you do these problems, a lot of students will say, oh, you beauty, this is a good start. This is pretty straightforward. But if you don't put the energy into learning all the terminology and then the maths becomes a bit more complicated, unfortunately, you'll be a bit confused, which is a problem. So, all right, so that's what so if you see a, a symbol and you don't know the meaning, find it out as you go and build up your notation knowledge. All right, so we expect the sum of the individual probabilities to add up to 1, and we expect the individual probabilities of the outcomes to be between 0 and 1. And that is the case, so that is a valid range of results. Just this is an introductory problem, and we'll come back and during the week you will practice doing these problems. But there's a definition of fair price, which is like within this situation of this statistics. A fair price is defined to be the amount that you expect to get back in the long run is equal to the amount you pay out. So the gain is zero. So what you pay out and what you get back equals zero is called the gain. So just watch out for definitions that are words that are everyday language, but we're using them with a special meaning. All right. So have a look at this problem. Just highlight it so that I know what you're reading. Yes, the variable x that we're looking for is the sum of the numbers. Now, would people like to try and explain if they believe that this variable x is a discrete random variable? What is it about it that helps to make it a discrete random variable? So look at this. We've talked a bit about random. We haven't talked too much about discrete, and we've talked a little bit about variable. So it's those three words together. Now, you don't have to do the whole explanation, but what are your first thoughts? And Callum, do you mind? What is your first thoughts? Do you think it's discrete or not? All right, Callum. So we're just looking at this situation with the two spinners. So each spinner is spun and we add up the number and we define the variable x as the sum of the numbers. Is it a discrete random variable and why? Now, Emmy, you get off scot-free unless you're going to text chat. Pete, do you have an opinion or a guess? All right, so the limited number of outcomes are the sum of the numbers 1 plus 1 is 2, 3, and if you do it consecutively, you get up to 6 plus 4 is 10. All right, so there's a countable number of outcomes. Now, I've changed your wording because if the number of outcomes is countable but infinite, it is still a discrete random variable. And there's a movie on the Moodle site that will expand or define it very clearly. So actually I haven't done this. I made the weekly work before I saw the link to the Moodle. So please make sure you have a little look at, I think it's about a 14-minute video that really clearly defines random and continuous variables. So that's something, it's got to be countable, but it can actually be infinite countable, which is sometimes a bit of a surprise. Yep. Okay. So I'm going to follow Pete's thought there, and I'd like Pete or any of the class members to sort of um, answer again. So if instead of having 2, I had 2.1, and instead of 6, I had 6.3, the outcomes would have a decimal in them. If those numbers were not integers, but they were a definite number, but they were decimals, is it still discrete? What do you reckon, Pete? Yes. Oh, that's true. But what we're saying is the reverse, that if you have decimals, it can still be discrete. All right, smiley face, everyone. So Callum and Emmy, do you understand that it's got to be countable? And I don't know whether the word finite countable helps. So 2.1 is a finite number. Uh, so let's just continuous is something that you can measure to more and more precision. So if the variable was the sum of heights of two members in a class, chosen from random, something like that. So it's a similar situation, but the variable we are measuring rather than counting. So often measurements are continuous. So time can be split up to more and more precise, or weight or height, something that we measure, or concentration. Though actually when you get down to concentration, because atoms are discrete, you could argue that concentration was discrete. All right, so sometimes when we get to huge numbers of tiny things, it looks continuous but is actually still discrete. All right. So the possible values of x, of the random variable x, is a set of numbers. So the curvy brackets is the set of outcomes. And I've begun to write them 2, 3, 4, up to 10. And the outcome is the little x. If we've got the variable we're interested in as capital X, then the variable would be little x. If we wrote the variable we were interested in as y, then we'd use little y. Okay, so you've got to be consistent between the two sets. Are we interested in anything other than the number of outcomes? Yeah. So are the probabilities of the outcomes equal? No. So the word distribution becomes very important. So in some probability sets, every outcome has equal probability. But in this particular one, to get a double number is much harder than to get a sum of 7, because the only way to get double 1 is a 1 and a 1. But to get 7, we could get a 1 and a 6, or a 2 and a 5, or a 3 and a 4, um, or a 4 and a 3. And therefore, the probability is 4 times higher. So if you were playing this game and you were savvy, you would be picking 7 if you wanted to win on the sum. So in probability and using probability data for prediction, the distribution is what quite often we're really interested in. All right, I'd like you now to read this question and see if you can work out the answers. So I'll give you a bit of time. Could you again highlight just so that I can see where you're up to in your reading? And you can help each other out. So the first thoughts, write them down, and someone might say, like you might get an idea from what someone else has written. Are any of you ready to write down the possible values of x? Focusing that x represents the number of games played in the final series. And sometimes to say a number and then say, no, it can't be, is not a bad starting point. So if I suggested one of the outcomes was 2 games, does anyone want to comment on that proposition? Yes, they have to play at least 4 games because we're interested in the team that wins, and um, it represents the number of games played in the final series. And the only way to win the final series is to have 4 games. Smiley face if you see that the lowest number has to be 4. That's winning all 4 straight off. All right, so now, Emmy, thank you for what you've written in text chat. Can anyone explain why Emmy stopped at 7? Now, again, think of the next number and there's a reason it's going to be rejected. So, what's wrong with having 8 games? Remember, as soon as you've won 4 games, the series ends. So, Emmy's explanation is superb. All right, do you feel confident now that it has to be 7 because you can't have 2 teams winning? You can't have 2 teams with 4 games. S- Light bulb, do you find, do you think, oh, yeah, that's absolutely makes sense? Do you feel a sense of, I like it? Um, if you had more than 2 teams, it would still be possible to have 2 teams with 4 games. So that is a really fair, yeah. So it's complicated. So often the definition of the situation, you've got to be really clear about it. And in this one, that consideration of 3 teams, is it still true? And sometimes you just say they haven't worded the question with enough clarity. And in statistics, the people who, if it's a real data collection, the preparation of how and why you are going to collect the data is absolutely crucial. Otherwise, the data is invalid. And people who understand statistics, they will say you are drawing conclusions that cannot be drawn because that data was not collected in a valid manner. And so there's a little saying that you may have heard: lies, damn lies, and statistics. Has anyone heard that? All right, so people who don't like maths, they tend to know that little saying, but it is true. You've got to set up the situation right. I'm really pleased to see um, the notation on the board, and that's something you're going to have to practice. The only thing with that notation, that the number of games is between 4 and strictly less than 8, it should be a lowercase x. All right, do you follow that? That the outcomes are the lowercase x. And that's why I really appreciate people writing their responses. Sometimes it's just, you know, you didn't think it through or you hit the wrong key, but sometimes it shows something that you haven't fully understood. Okay, so we've already mentioned that the distribution is important. So I just want you to look at that information both in a table and in a column graph. Is it easier to understand the information, or is the same information presented in both formats, in the table and in the column graph? Same information. Callum, are you willing to make a comment? Do you think the same information is presented? All right. So what do we see from those 2 formats? I'll just quickly mention things that, and you just give me ticks and say, yes, I can see that. Yes, I just haven't written it yet. All right, when I look at the table, I see that there are three outcomes, 0, 1, and 2, and I've got to go back and read what my characteristic is, my variable. So my random variable is the number of heads. So that means 0 heads, 1 or 2 heads. And that the probability of getting 0 heads is a quarter. So I can see by the numbers that it's symmetrical. Personally, I can see the symmetry, especially if the table had like 20 outcomes. I can see the symmetry, or if it was skewed, more easily on the graph. And probably the most frequent outcome, I can work it out from the numbers, but I can actually see it. The most frequent is getting 1 head. Do you agree that some things visually, the information is on the table, but seeing the visual, the clarity's better? Do you agree or disagree? And I guess sometimes it depends on how complex the data is. Okay, that's all I'm going to do with this one. Now, earlier on, I mentioned some things about valid distributions. If you look in the green box, is Callum or Pete willing to read out the first sentence? And it means that you need to understand what the notation is saying. All right, let me have a shot then. If x is a random variable with possible values, the set x1 through to xn, where n is the number of outcomes, with the corresponding probabilities, the set of probability 1 matches the outcome 1, such that the probability of obtaining each of the outcomes equals their individual probabilities. Then the following is true. So that actually was a little bit complicated. So can you see how I sort of enriched what was there by not just reading the symbols, but putting the meaning onto the symbols? And that's what you need to do in the weekly work. All right? So give me a tick. When you do the weekly work, do you struggle, your brain struggle with interpreting the symbols? Yeah, it's important. And then after you've done that initial struggle, it's no longer a problem, hopefully. So now, for it to be a valid random variable distribution, the probabilities need to lie between 0 less than or equal to 1, the sum of the individual probabilities equals 1, and it's made up of the set of the individual probabilities, makes up the distribution. Sorry, I haven't written it down, but it is there. I think the top bit is a different page to the bottom bit. So, Emmy, is this too small for you to read? I'll open up my online textbook and see who can find it first. So we're in chapter 7. Has someone found a page? Let's see if it's 7b. Yes, it is. Excellent. So that's page 187. So thanks, Pete. So now, using that definition of a valid probability distribution, Can you look at the brown box? Is this a valid probability distribution? The function, see P of X, this is now a function. So capital P is for the function in terms of X, is X squared plus 1 on 34. And the outcomes, the individual outcomes are the values of X from 1 to 4. So let's put the values in. 1 squared plus 1 is 2 on 34. Now I'm actually going to leave it on 34 so it's easy to add them all up. If you put 2 in, you get 5 on 34. All right, so I'll give you a minute. You might use your calculators, you're welcome to. We're expecting it, if it's valid, it's going to add up to 1. Yeah, so the individual probabilities are between 0 and 1, and the sum of the probabilities, the individual probabilities, does add up to 1. And we have written as a set of outcomes. So the probability distribution, so the last dot point is the set, so the set notation, the curly brackets of the probabilities. Now, technically you should cancel them to the lowest fraction or write them as a decimal. All right, so I'll put that as 1 on 17. Oops, not plus, comma, because it's the set of outcomes of probabilities. And 10 on 34 cancels to 5 on 17. 2 sevens are 14, and the last one's a half. And I've accidentally written plus. I should write a comma. So this is the sort of thing that is important. Make sure that your notation's correct. Okay. All right, so the last one is looking at a magazine store and presenting the data in a table. So if you read on the left, they're promoting their magazine store and they anticipate triple the number of customers. Have you got any idea how you would use the data to decide how many magazines to buy? All right, yeah, you got an idea there, Pete? Exactly. Yep. All right, so we've got that data about the past in the table. So adding on to what you started, Peter, and I know I cut you off a bit, is that we could work out the average magazines sold by doing 1 times the probability, 1 times 0.23 is 0.23, and adding it all together, 2 magazines times 0.38, and finish it off. Now, I think it's between 2 and 3 magazines, so I don't know what the answer is. Let's say it's 2.6 magazines in the long term. Now, if you're buying thousands of magazines, it does not matter that you've got a decimal in this answer. Can you see that? So if you've got 1,000 customers, you'd multiply that by 1,000 and you'd say that every week you would on average need 2,600 magazines. And if you're going to triple the customer base on your promotion day, then you're going to have to multiply that by 3. So that's partly just to try and help you understand how the statistics can be predictive. Now you don't get it exactly right, and the distribution, you wouldn't want to just buy the total of magazines. You'd actually want to keep it in the distribution of the type of magazine that is sold. So you'd need more data to run your magazine shop than simply the number of magazines. But that you might want to know that for the amount of money you need to outlay rather than actually the magazines that you're going to buy. So I hope I've given a bit of connectivity with why we have the data and how it might be used. So basically, I believe that the work during the week, I suspect you're going to find it pretty straightforward. But in the weekly work, I've also got make sure you correct the set that most students did in the last week of last term, and just a couple of students. Nikki was overseas for a fortnight, so she's doing hers this week. So there's a couple of students who haven't done it yet for personal reasons. Any questions or comments before we finish the lesson?